see this example. In this example, the problem is like this. A control system is shown in the figure. Find stability of the closed loop system when g of s is equal to, first case, 10 into s power s plus 1 divided by s square into s plus 2. This is the first part of the problem. Second, same g of s is equal to 10 into s plus 2 divided by s square into s plus 1. And what will be the block diagram? The block diagram is like this. It is a unity feedback system and the g is here, forward path transfer function. Then we have r input and summing point, negative feedback, and I have c of s. So whatever g of s that are given, which are the forward path transfer function g and the feedback path h is equal to 1. So we need to find the stability of these two systems. Now how to solve this using the Routh-Hurwitz criteria? When you look at these two transfer functions, there is a slight relation. What is that? The first one, 10 into s plus 1 divided by s square into s plus 2. So we know that the numerator roots are zeros of the g of s, denominator roots are the poles of the g of s. Now for g of s, I have 1 0 at s is equal to minus 1. There are 3 poles. Out of 3 poles, we have 2 poles at origin and 1 pole is s is equal to minus 2. So 1 0 s is minus 1 and 1 finite 0 and 1 finite pole is s is equal to minus 2. But in the immediate next one, these 2 poles and zeros are interchanged, which means the location of pole has come 0 and 0's location is occupied by the pole. Therefore, it is 10 into s plus 2 divided by s square into s plus 1. What happened when you interchange the location of poles and zeros? Clearly, we can find the stability. Now, so we will take the first case. What is the first case? The first case is g of s is equal to 10 into, if you directly multiply, that becomes 10s plus 10 divided by s cube plus 2s square. So in RH criteria, we need to write the characteristic equation, which is 1 plus gh is equal to 0. Sometimes the characteristic equation will be given to you. So if it is given to you, directly we take the coefficients and we fill the Routh array. But sometimes only gh of s will be given, or sometimes closed loop transfer function is given. If closed loop transfer function is given, directly take the denominator. If open loop transfer function is given, then we need to write 1 plus gh is equal to 0. So I am writing the same thing, 1 plus gh is 0. Therefore, you will be getting it as s cube plus 2s square plus 10s plus 10 is equal to 0. This is the characteristic equation. The highest degree is 3. Therefore, we can easily form the Routh array. Then we can find the stability of the system. Let us see how to do that. So let us take our Routh array. You have this is Routh array. The highest degree is s cube and s square, s power 1 and s power 0. And the first 2 rows will be filled from the coefficient of the characteristic equation. We have 1, 2 and as well as 10 and 10. Then what will be the next row? Next row is s power 1. How do you calculate that? 2 into 10 minus 10 into 1 divided by 2, which results in 5. What will be the last element? It is directly, will take 10, because here I have 0, this 10 is directly carry forward here. Then we will have all 4 first column elements. So these, if you look at the first column elements, then we don't have any sign change in all the elements. We have all positive signs. So when you have all positive signs, we know that there are no poles in the right half of the S-plane. All 3 poles are in the left half of the S-plane only. So that particular closed loop system is stable. Second example, we have again we can do the same thing. 1 plus gh is equal to 0. 1 plus whatever the transfer function we have, 10 into s plus 2 by you have s square into s plus 1. We can substitute and we will be getting the characteristic equation as s cube plus s plus 10s plus 20 is equal to 0. A similar way, we can form the Routh array s cube, s square, s power 1, s power 0, and the first 2 elements are 1, 1 and 10, 20. Then you can find out the third row element 1 into 10 minus 20 into 1 divided by 1. So which gives us minus 10. What will be the last element? You can directly take the 20 here. So my first column elements are 1, 1, minus 10 and 20. Now look at here. So from first element to next element there is no sign change. For next element to minus 1, 1 to minus 10, yes, there is one sign change. Minus 10 to minus 20, yes, there is one more sign change. Therefore, total number of sign changes is 2 and we know the total number of poles is 3. Therefore, out of 3 poles, 2 poles are lying in right of the S-plane. There is only one pole in the left of the S-plane. My closed loop system is unstable. Therefore, when you observe these two transfer functions, so the first transfer function, the system is stable. The next second transfer function, system is unstable. That means whenever you interchange poles and zeros, there will be some effect in the closed loop stability of the system. So in the two examples, we have seen how to find the stability using a Routh array, and in all the problems we have first elements with either all same sign or we have some sign changes. There are two special cases in Routh's array or Routh-Hurwitz criteria. What are the special cases? Special case 1. If the first element of any row is 0 with all other elements are non-zeros, then to proceed further, replace 0 with epsilon is a small positive number where epsilon tends to 0. Epsilon is very small positive number, and fill the complete Routh array. And to know the stability of the system, look at the again first column elements and their sign changes. So what happens when you have the first element of any row is 0? So if the first element of any row is 0, when you are calculating the next row elements, we need to take some calculation divided by the first row elements. So that gives the infinity, right? So then we cannot proceed further. So to remove that obstruction, then what we are doing is replacing 0 with epsilon. And remember, in this case, I will have only one 0 element, that to be in the first element. All other elements of that row are non-zero, right? So this is a special case 1, and what will be the solution? I said replace 0 with epsilon. Epsilon is a very small positive number, epsilon tends to 0, and do the calculations and fill the Routh array completely with the help of epsilon only. Finally, substitute limit epsilon tends to 0 wherever epsilon is there, and find out the first column elements, look at their signs, which will give us how many sign changes and also how many roots of the characteristic equation are having positive real part. From that you can find the stability of the system. Now to illustrate this special case 1, let us look at the small example. Now in this example, find the stability of the system whose characteristic equation is given by Q of s is equal to s square plus s plus 2 is equal to 0. To illustrate the special case 1, let us look at this example. So in this example, find the stability of the system whose characteristic equation is given by sq plus s plus 2 is equal to 0. sq plus s plus 2 is equal to 0. When you look at this characteristic equation, there is one term which is missing. I have s cube, s and s power 0, s square term is missing, which means directly we can say that particular system is unstable. But if we want to know how many poles that are lying in right of the S-plane, then we need to form the Routh's array. Okay, so let us look at that, how many poles that are lying in the right of the S-plane. We know already the system is unstable. Now when you take the Routh array, again here we have like this, and this is nothing but your s cube highest degree and s square and s power 1 and s power 0. Very simple example. So you fill s cube and s square rows with the help of the coefficients of the characteristic equation, which goes, this is 1 and s square we don't have, therefore that is 0. Then we have 1 and 2. So 1, 1, 0, 2 are the elements of first two rows. Now when you are trying to calculate s power 1, then we have 0 into 1 minus 2 into 1 divided by 0, which gives the infinity. So that is a special case abstraction. Therefore, what we need to do is we need to replace this 0 with the epsilon. Let us replace this with the epsilon. Okay. Next, so what will be the s square now? S square elements are epsilon 2. Then s power 1 elements, then we can calculate epsilon into 1 minus 2 into 1 divided by the epsilon. That means epsilon minus 2 divided by the epsilon. The next element is anyway it is 0. What is s power 0? The 2 is directly carry forward here. The s power 0 element is 2. Now to find the stability, we need to look at the first column elements. Now here first column elements are, if you write the first column here, so that is 1 epsilon, then we have epsilon minus 2 by epsilon and 2. So 1 and 2 it is okay, they are both positive, and then epsilon I said it is a small positive number, therefore that is going to be plus 0. So we should look at here epsilon minus 2 by epsilon. We need to apply limit epsilon tends to 0. So when you take this alone, s power 1 term, so s power 1 limit epsilon tends to 0, epsilon minus 2 by epsilon. We can write epsilon by epsilon is 1, therefore 1 minus 2 by epsilon. Then you substitute epsilon 0, 1 minus infinity, 1 minus infinity is a minus infinity. So what will be the term that you are getting here for s power 1? It is minus infinity. So now if you look at all the elements, now all the elements are 1, you have plus 0, then minus infinity and plus 2. Then what are sign changes? 1 to plus 0 is no sign change, plus 0 to minus infinity there is one sign change, minus infinity to plus 2 is another sign change. Therefore, there are two sign changes, but highest degree is 3, there are total number of poles 3, and two sign changes means 2 poles in the right of the S-plane and 1 pole in the left of the S-plane. As I said in the starting, the closed loop system is unstable.